Digital filters are one of the many applications of the Fourier transform, the Swiss army knife of digital signal processing. The rise of smartphones, wearables, remote monitoring, and the Internet of Things has massively increased the need for digital filters to tease ever more useful data out of often very noisy signals from the sensors mounted on these devices. There has therefore been a massive push to make these filters better, quicker, and more intelligent. We've covered a lot of the theory behind how the Fourier transform works on this channel, and we'll be looking at how digital filters work in future videos. However, as an introduction, I want to go beyond the theory and look at how digital filters are designed and used in practice. To that end, I am joined in this video by a guest who is an expert on digital filter design. Hi, I'm Mark Newman, and this channel is all about helping you understand the fascinating world of signals and systems. I'm joined by Dr. Sanjeev Sarpal, an internationally respected artificial intelligence tech leader and expert in digital filter design. Dr. Sarpal is the founder and director of ASN, a company that specializes in the development of AI algorithms for Internet of Things enabled devices. He has worked extensively with digital filters in all manner of sensor applications in a wide range of industries, advising international companies like Arm, IBM, and Microsoft on their AI algorithmic digital technologies. He is also the inventor of the ASN Filter Designer, a real-time filter designing tool. Sanjeev, thank you very much for joining us.
Thanks for having me.
You've been in the field now for some 25 years. You must have a lot of practical experience of many different types of signals. Please tell us about yourself.
Yeah, sure. Well, I'm the founder and director of ASN, and I lead our AI and embedded software teams. Started off my career as working as a hardware product developer, and then after getting a PhD in signal processing, working for Mitsubishi Electric as an algorithm developer in their European algorithmic development laboratory. I got to work with some pretty top signal processing people. So that's where I got my kind of first taste of it all. And then thanks to my experiences there, I've kind of built up all of those skills over the years, and I've come up with about 25 smart sensor products for various international clients. So that's what we primarily do at ASN these days.
How did you get into the whole field of digital filter design in the first place?
It pretty much started off from a vague lecture during my bachelor's. The lecturer presented the theory of designing an IIR type filter, but didn't really have access to any tools or practical examples. When I asked him all these questions, I'm not really sure he understood it himself. He struggled to answer pretty much any practical questions of where would you really use this kind of technology, and how do you actually specify the parameters for the designs? A lot of my kind of fellow students shrugged it off, thought, oh, well, it's just something we have to learn for the exam. But I decided to, I really want to learn this. I was absolutely fascinated of how you could filter signals in software rather than the way we were taught, which was using resistors and capacitors and trying to filter analog signals. So in the coming years, after I completed my studies and started working in hardware, I invested in a TI DSP starter kit, which was quite affordable back then, quite amazing really. And then this had a massive learning curve. I mean, their documentation was so dry, it was terrible. And I studied control systems engineering, so we weren't really taught anything about embedded programming. So I had to break my head for many, many years there. I went into it and I thought, oh, this is really interesting. And then I decided to write my own first digital filter design program in Turbo Pascal. So it was all done in DOS, first in Windows. And in order to plot things and get a Fourier transform, I had to use Excel, because that was the only thing that was available. I didn't know about the LAPACK math library that was available since the 1970s, but I didn't know about it. But I spent, a good number of late nights working on this thing and then showing to my colleagues what I'd done. And they were all really amazed. It was like, wow. And I thought, yeah, I mean, you design these filters, but then you want to do something with them. So I came up with a really simple kind of C code generator as well for really simple type of filters. And then that was the kind of first attempt that I had of doing this type of stuff. And that was almost 25 years ago. Then I kind of left it and did a few other things. And then I was given the opportunity to start the PhD in 2003. And then I had a really cool supervisor who really understood the theory, and he was a great sparring partner. So he filled in a hell of a lot of the gaps that I had. So it just gave me more and more and more inspiration over the years. And with the advent of other tools, I mean, the MathWorks, they came up with Filter Design Toolbox in 2000. And that was just an amazing moment for loads of developers. They were like, wow, a graphical interface that was coupled with MATLAB, and you can do all kinds of things. But when I think back to that, that was 22 years ago, and they're still using the same thing. So that's kind of over the years, I thought to myself, I'm sure I can improve on this with all the experience I've built up and all of the modern kind of app technology that's available today. So that's what inspired me to start up the development of the Filter Designer program.
I find it very interesting that you said that you felt when you were learning this stuff at university, it was just too theoretical with no view how the principles you were learning could be applied in practice.
Yeah, I mean, I think, my lecturer, I mean, he was such a sweet guy. He was a mathematician, and he was someone who was brilliant at mathematics, and he had a tremendous amount of patience as well, but he just was not practical. So when I kind of asked these practical questions of, okay, I understand what you're saying, but where would you use this then? Where are the practical applications, and how do you actually specify all these design parameters? I mean, how do you know what the hell to fill in? Where do you begin? And he was just a little bit lost. He was like, well, yeah, mathematically it's beautiful though. I thought, well, it doesn't really help a lot of people working in industry. So I've always had that practical thing in my head of, mathematics is great, but you really need to apply it.
Focusing in on the practical side, where are we going to use digital filters? I mean, what are they used for?
Yeah, I mean, there are loads of applications these days. I mean, everybody's talking about AI and IoT and sensors and that kind of stuff. But when you get down to the nitty gritty, a hell of a lot of sensors, they need some kind of filter in order to pull out the wanted information. There's always noise and interference. I mean, if you think about, power line interfering with something, if you're working with ECG type data, that's something that's a big deal. When you're looking at trying to remove baseline wander on data, how do you do that in real time? How do you do that in a kind of simple way as well? These are where digital filters come in. So yes, I mean, even though we use AI very heavily, we have a tremendous amount of traditional signal processing in order to pull out these features of these signals in order to help the AI algorithms do their things. So there are hundreds of examples I can go through: audio, biomedical, industrial temperature sensors, gas sensors, everything like that. It's not just limited to just cleaning up and enhancing data, comes down to pulling out meaningful information and then throwing away the information that you don't want, but then also having a certain amount of, I would say, experience of saying, okay, we know this is a delicate signal, it's feature rich, and applying data to that, applying a filter to that will destroy some of the vulnerable pieces of information in there. ECG, biometrical data, is a very good example of that.
So you have to be careful how you apply your filter.
Yeah.
What would you say are the advantages and disadvantages of digital filters versus analog filters?
Yeah, this is something that I remember I asked my my lecturer on the first time. I said, why do this? I said, if you just get some resistors, capacitors, you can do it the same. I remember sitting in the lab with another group of students and whatever, and we were kind of talking about this, and we thought, why bother then? Because you can do everything in analog. And then it wasn't until we started experimenting and trying stuff out with various configurations that we actually kind of found out that, wait a minute, if you just want to have a simple low pass filter, you just have in analog, you just have one resistor and one capacitor. Okay, that's great. It costs nothing. It's easy. Anybody can do it. But then you thought to myself, well, wait a minute. You got tolerances on these components. So if you're going to make 100 of these filters, they're all going to have different characteristics because they've got component tolerance. And that was when I started to think, I thought, well, wait a minute. Yeah. Digital doesn't have that problem. It's all controlled by a crystal oscillator inside the processor. So if you want to produce 100 of these types of filters, they'll have exactly the same characteristics. And that was the kind of eureka moment. I thought, now I understand that. And yeah, digital is very flexible as well. If you today say, okay, I'm going to connect this type of sensor and I want this kind of filter performance or this kind of shape, you can just basically reprogram it with a new set of coefficients. If you did that in analog, you'd have to get your soldering iron out and butcher the board. So it's not really ideal there. The biggest advantage of analog is that it's low noise. That digital creates much, much more noise. And if you're dealing with really, really minute signals, then that can become a problem. There's only a limit to the amount of filtering that you can actually do before you actually destroy a signal completely. So analog certainly has its place. It's very cheap. It's easy to do simple types of filters, and it's low noise. Digital, I would say, has this flexibility and reproducibility. And that I would say is it's big plus there.
Are there things that you can do with digital filters that you can't do with analog filters?
Well, I would say that when it comes to there are two types of digital filter. There's the FIR and the IIR. Now, IIR type filters can be created from an analog version type filter. So that was why they were very popular to begin with. But these newer, I should say, they've been around for a long time. These FIR filters can have exactly linear phase. Now, you'd say, why is that important? Well, linear phase has the advantage of not warping or distorting the signal. So if I go back to biomedical again, or anything whereby you say, I want to keep the shape of that, but I just want to take off some of the noise, you put it through one of these linear phase filters, which is only possible with one of these FIR type filters. It's incredibly difficult to do with the IIR type filters, even though there are a number of tricks, but it's not very, very easy to do at all. So that is one of the biggest pluses there, I would say.
Can you be more precise with a digital filter? I mean, you mentioned component tolerance, but can you also better control how sharp the roll-off of the filter is?
Yeah, I mean, I would say if we go back to these FIR type filters, what you can actually do is you can specify a desired frequency response. So from your magnitude and phase, you'd say, this is what I want. And then it will design an equivalent FIR type filter. So it has that flexibility. In terms of accuracy, yes, you have this implementation that is done by a crystal inside of a microcontroller or on a computer. So yes, it's very reproducible and accurate in that respect. In terms of customizations, and I think this is probably something we'll see with the ASN filter design later. I mean, nudging the poles and zeros of a digital filter is much more easier than actually saying, okay, I just want it slightly to the left or slightly to the right of null. You can't really do that with a component. It's a case of it is what it is. If it says 10 nanofarads, then it's 10 nanofarads with a certain percentage. That is, if you want to call it a disadvantage, and with a digital filter, you have that high level of flexibility. Accuracy, this is something that I remember speaking to various analog gurus about this, because I got really annoyed that when they hear that people say digital is more accurate than analog. I think it comes down to putting down all of the aspects of what it is you're trying to do. Analog is not per se less accurate. Analog can be incredibly accurate. It just depends what it is you're trying to do. When you actually consider a poor digital implementation whereby you see lots of clock noise on the signal, or you see other kinds of digital noise on the signal, your filters can be the best in the world, but then you've got lots of noise. If you're running some instrumentation electronics in analog, and you're running it off a battery, let's just say, which doesn't have any noise and it's all compact, then you'll be surprised of how clean the signal is, and then you can do further processing on that. So it comes down to the fact that I've seen some ingenious designs over the years that still use analog, simply because it's better than digital for certain things.
So the perfect world is this happy medium between some analog filtering and
Yeah.
some digital filtering.
Yeah, I would say so.
And of course, we're never going to get away from analog filters completely,
No.
because before we can even sample our signal, we have to take off the frequencies above the Nyquist rate. So
Absolutely.
analog filters are always going to have their place.
Absolutely. Yeah, absolutely. And I think, it's a case of people have tried to kill analog for years, and it keeps on coming back up. But then it comes down to the fact of what it is you're trying to do. And as you said, the preparation, the anti-aliasing filters, there's nothing better than a good old analog filter for that. And there are various other applications of, simple control applications whereby you think, okay, you can do this with a few analog components, with an operational amplifier and some feedback loops, and you don't need a digital controller. So it comes down to, what it is you're trying to achieve. But I think also, I guess with the older engineers, how stubborn you are as well. I mean, some of them really want to stay in that world and say, yeah, well, I'm not interested in all this digital stuff. But it is changing. And I think, certainly a lot of younger engineers think that, yes, digital is more accurate and analog is just, that's what we did in the past. But I would say to any young person listening to this, take a moment and have a look. It is certainly worthwhile having a look at analog solutions and how you can augment them with your digital type solution.
So what are some of the practical considerations we need to think about before we go into designing a digital filter?
Well, I mean, I think that the most fundamental question is, what information do you want to keep and what do you want to throw away? So using like a Fourier type analysis on data, you can actually see parts of the spectrum that you want to keep and then parts of the spectrum that you want to throw away. Do you have any kind of a priori type of information? So if you think about power line interference, then okay, that's 50 or 60 hertz. Well, we don't want to get rid of that. But then is there anything that's nearby to that? Or are there any kind of situations that something that you're interested in overlaps that? What are you going to do in that case? So those are that's the first step, I would say. And then you need to think about what sampling rate do we need? Now, you shouldn't actually implement a filter just at twice the Nyquist rate. It's a case of, do you go 10 times higher? Do you go 20 times higher? Do you go 5 times higher? It just depends upon your application. And then bearing in mind, the higher that you're sampling, the more coefficients you may need for a low cutoff. And then it's more data. So there's a trade-off there. And then once you've answered that, then you go to an interesting question of which type of digital filter do you need? Do you need an FIR type filter or do you need an IIR type filter? Now, once again, there's a trade-off with the amount of coefficients, latency, group delay, that kind of stuff. It all comes together. And so there is a certain amount of homework that's required even before that you actually start designing anything. You just say, okay, I just need a sanity check of what it is I'm doing. And then you come to the fundamental question then of where I got stuck originally of what specifications do we need then? If you say, all right, we're going to use an IR filter then. So what type of IR filter then? Are you going to use a Butterworth? Are you going to use a Chebyshev? Are you going to use an elliptic? Are you going to use a Bessel? Oh, what filter order do you need? How do you specify the stop band and pass band attenuation for your specific case? So these are all things that add up. And then you think, well, how am I going to answer that then? And that's where you need modern tools whereby you can actually try out various configurations and the tool will give you the answer of saying, okay, this is roughly what you want. And this was the primary concept behind Filter Designer originally. What we thought of was that you basically have a data set, you have something you want to filter, you say roughly, okay, I roughly know what my sampling rate is. I think I want an FIR filter, and I know roughly what I want to throw away, and I just want to play with it on the data, just see how it looks. And that's basically the concept behind the Filter Designer. And this all works in real time. So it gives you the results in real time, and it gives you the filtered results in real time. And that I would say is a very important step. And then finally, it's a case of where are you going to implement it then? So is it going to be implemented on an embedded processor as a desktop application? Where exactly? So what code would you need in order to run that then? Is it all going to be run in Python, or is it going to be run in C, or I don't know, in MATLAB or something like that? Those are considerations. Most people these days will have some kind of cheap development kits from ST, for instance, or a few others. They make some really great starter kits. And then it's a case of you just say, okay, I've got some sensor data. I just want to play with it. and I just want to do a little bit of filtering, but I don't understand the libraries and all the APIs that come with it. So that was also something that we heard from various clients, and we included in this filter designer tool.
So you just mentioned the ASN Filter Designer. What drove you to develop it? What was it that was missing from the current tools out there?
I think it goes back to the university days I was mentioning in the 90s. The only tools that we really had were Microsoft Excel and DOS programs. And then these interfaces were just so nerdy, slow. There was no graphical support really, and you couldn't really use them without figuring lots of theory out. So I think things changed in 2000 when the Filter Design Toolbox came out from MATLAB, as I mentioned earlier. This was a really big step forward whereby you had a graphical interface, and they really did their best to try and simplify it. But it still had this kind of old design paradigm, as I call it, of entering specifications in a text box and then clicking on a design button. So then it was still that question of what specifications do I need to enter then? I don't know. Tell me. So that was basically one of the great motivations behind it. And I thought, always in the back of my head, I carried on doing signal processing consultancy for a good 15, 20 years. And I thought to myself, there's just got to be a better way of doing this. So then I thought around 2010, I said, right, I'm going to make a start on designing a new filter design program based on these years of experience and frustrations that not only I had, some of my colleagues as well. So we looked around and then we found Intel's math kernel library, which is based upon LAPACK and a few other things. We used that as a foundation, and then we put all of our algorithms and knowledge on top of that as a separate layer. And then we had our collaborations with companies such as ARM. Most of the embedded processors in the world are based upon ARM technology, even though there are various silicon vendors. They all use ARM IP. We joined their ecosystem, and we basically came up with this paradigm of filter design, all graphically based, real-time design environments, simulation environments, and then deployment to ARM processors.
So the big things you felt were missing were the intuitive graphical interface, the real-time processing showing what the filter is actually going to do to the signal, and the code generation and export, enabling the developer to quickly implement the filter in their design.
Yeah, and I think also getting it all to work in real time is that was really tricky. And going through all of the efficient implementations in C++ and all these things, we studied loads of them, and we've been using them for other projects over the years. So packaging it all up into one tool, and then making it available to the community is a big motivation behind it all as well.
So let's see the filter designer in action with a practical demonstration. If you own a Fitbit, you've probably noticed this flashing LED that is pressed against your skin whenever you wear it. But what is this LED for? And how does it enable the Fitbit to extract important biomedical data from your arm? Over to you, Sanjeev.
Thanks, Mark. Advances in telemedicine healthcare products over the past decades have been truly miraculous, with ingenious little devices invented by startups as well as by large corporations, for example Apple's smartwatch and the Fitbit. But how do you design wearable devices to accurately measure biometric data in everyday life with low-cost sensor technology, such as when someone is going about their daily routine? At the center of all wearable smartwatch technologies is a PPG sensor that is used to measure pulse rate, stress, and other biometrically important features. When considering PPG pulse measurement, a simple LED and photodiode setup is used to measure the reflected light from blood flow under the skin. When plotting this data over time, we obtain a dataset with peaks and subpeaks, as well as some noise. In the simplest application, the challenge is to find the position of the larger peaks in the dataset, and then based on the relative time difference, calculate the pulse rate. Sounds easy, right? Well, let's analyze this dataset. An intuitive step forward to finding the local peaks will be first to remove the dataset's mean. As a majority of PPG sensor applications use a unipolar range ADC in a low-cost microcontroller, this is a logical step in order to define a detection threshold with respect to 0. After removing the mean and defining a suitable detection threshold, the next step would be to scan through the whole dataset with a narrow width analysis window looking for the local maximums above the detection threshold. This seems to have worked very well, but in reality, arm and torso movement, the effects of skin color and skin dryness affect the amplitude of the measured peaks, and creates more measurement noise, including an annoying wobble of the whole waveform, the so-called baseline wander problem. Clearly, our simple peak detection method doesn't work here. So what can we do about this? It would be valid to high-pass signal the filter to remove the low-frequency baseline wander, but designing a suitable high-pass filter with a low-frequency cutoff at a high sampling rate typically found in biomedical applications has its problems, as a linear phase FIR filter requires a large number of coefficients, typically more than 1000, leading to large latency, and the nonlinear phase response of IIR filters alters the shape of the waveform, which may warp the positions of the peaks. Therefore, let's have a look at the properties of the signal that we want to analyze. We know that baseline wander is very low frequency, typically less than half a hertz, so it's very slow moving, and that our PPG peaks have an instantaneous gradient of 0 at their maximum and minimum values. Therefore, if we differentiate the dataset using numerical differentiation, we should be able to find the location of our peaks. Let's look at a concept of this on an ideal signal with no noise. As seen, numerically differentiating the dataset, that is, subtracting the current value from its previous value assuming a monotonic time index, we obtain the waveform shown in red. Notice that the derivative waveform looks like an S shape around the peaks and troughs, and that the 0 crossing points coincide with the locations of these peaks and troughs. Analyzing the region around the 0 crossings, we see that the peak is actually defined as a down crossing, and a trough as an up crossing. In practice, due to glitches and measurement noise, the derivative data may not transition nicely through 0. So 0 crossings detected with bipolar detection thresholds is required for robustness. Okay, let's add some baseline wander. Great, the method seems to have worked very well. But now let's add some noise. How's this possible? Well, looking at the frequency response of a simple differentiator, we see that it's just a single 0 on the unit circle at DC. This is good for removing low frequencies, but as seen on the frequency response charts, the higher frequencies, greater than 20 Hz in this case, are actually amplified, which is why the noise is so dominant in our output waveform. Okay, you're probably thinking that if we can cascade a low-pass filter with a differentiator, then we can tame the noise. Well, let's have a look. Cascading a moving average low-pass filter with a differentiator, we see that we can indeed improve matters. This is now starting to look good, but it's still a little bit noisy. Therefore, what we ideally want is a filter that combines the differentiation action with low-pass filtering. Let's move over to the ASN Filter Designer UI. Clicking on the FIR tab and looking at the design methods, we see that the Parkes-McLennan algorithm supports a differentiation method. We can use this method to design our filter. Ordinarily, this would be difficult with traditional design tools, as you would need to explicitly enter design specifications before beginning. One obvious problem then would be, how do we define these specifications? ASN Filter Designer's high design efficiency overcomes this problem by allowing us to experiment with the magnitude specifications graphically, while letting the tool calculate the necessary design specifications in the background, all in real time. Realizing that the typical bandwidth of a PPG application is about 20 Hz, we can set our upper cutoff frequency to around 20 Hz. Notice that it's quite straightforward to design our filter by clicking and dragging on the red design markers to meet our specification, and that the real-time update means that we can instantly assess the design filter and tweak it as required. Let's now see how well this filter performs on our dataset. Importing the dataset into the signal analyzer and tweaking the specifications a little more, we can instantly see the effects on our dataset. That now looks pretty good. As a final step, we can deploy our filter to MATLAB, Python or C# for further algorithm development, or even to an ARM Cortex-M embedded processor for direct use in our microcontroller smartwatch application project via the tool's built-in code generation wizard.
Thanks for that demonstration. You're obviously trying to push the boundaries of filter design with this tool. Where do you see digital filters going in the future?
Oh, well, I think, as we said, earlier on, I mean, they'll always be there. You'll always need like an anti-aliasing filter, in analog, for instance, and it'll be just like our digital filters. Everything's going towards AI and deep learning and that kind of stuff. But I mean, these techniques, they are great, but they're computationally expensive. And I also think in order for AI is not as intelligent as a lot of people think it is. It does basically need support from simple things like digital filters in order to pull out meaningful features from the data in order to actually be beneficial to the end application. So I see digital filters moving on. They will join the world of AI, I think. I mean, people are talking about kernel type filter, other type of kernel filters, which are basically just doing the whole filtering operation in AI. Okay. But I think there'll always be the cases, everything's low power and wearables and batteries and that kind of stuff. There are always going to be a number of people who want something which is simple, low power, and they can just basically tinker around with and they can get it up and running. So I think digital filters will be here for a very, very long time.
Well, thank you very much for introducing us to the world of digital filters and for showing us the ASN Filter Designer. If you're interested in trying out the Filter Designer, then there is a link in the description below. So, how do digital filters work? And what has the Fourier transform got to do with them? As Sanjeev said, there are two main types of digital filter: FIR, or finite impulse response filters, and IIR, or infinite impulse response filters. In the next video, we're going to investigate these filters further by looking at a certain type of FIR filter that you may well have used before without even realizing it. We'll also be using the Fourier transform to look at the relationship between the frequency response of a filter and its impulse response. What is the nature of that relationship? And what is an impulse response? You'll find out in the next video. Let me just leave you with this thought though regarding digital filters. A multiplication in the frequency domain is a convolution in the time domain. Think about it.